Everyone. My name is Rafid Molla. I am a graduate student in the Department of Chemical Engineering. And today we're going to go over a few problems on extended surfaces or fins. And we're going to be looking at how to derive the differential equation or governing equation that describes the temperature profile in the fin for different kinds of geometries. So this kind of problem or this concept, this is something you guys might encounter if you're a mechanical engineering student studying heat transfer. So maybe in ME4210, or if you're a chemical engineering student, you might encounter this in transport phenomena too. So how do we get started on solving this kind of problem? So first off, what is an extended surface really quickly? So it is exactly what it sounds like. So it's just some object that's protruding from some kind of base material. And all it's doing is it's providing a larger surface area to increase the cooling or heating of this base material where this fin or surface is extending out from. So it's increasing or increasing the effectiveness of heat transfer to the base itself. When solving these kinds of problems, what you'd want to know is the thermal conductivity of the material. And usually there's convection going around a fin or extended surface. And what the convection is doing is either heating up the fin or it's cooling it down. And usually what you'll know is the temperature of the surrounding, let's say air, usually it's air cooling down some kind of fin. And you'll know the heat transfer coefficient. And also, once you have the differential equation, you might then you want to solve it and apply boundary conditions. So typical boundary conditions you might see is that the temperature of the base itself, and also if you have a fin that has an exposed surface at the end, you could say that side is insulated. So meaning there's no heat conduction once the fin reaches once you travel down the end of the fin. So first, let's set up a coordinate system. So in this kind of problem, this is usually a 1D heat transfer problem. We don't care about what's happening in the other direction. So here we have a cylindrical fin. I should have mentioned that. So in usually cylindrical geometries, you have a z direction, a radial direction, and in theta or angular direction. So typically in fins, the direction that you care about is the one that's down the axis of the fin, because that's where heat is conducting from the base. So the heat isn't like if you imagine how the heat is trying to flow through this object. If let's say this is really hot and the air is cold, so it's cooling down the fin, then you'd think that the heat is flowing down. It's not really flowing up. It's not spinning, or it's not going out radially. So generally, we say that the heat is flowing down the axis of your fin, and so it just turns into a 1D heat transfer problem. So how do we find that governing equation that describes the temperature profile here? So what you use is this technique of applying a differential control volume, and you perform an energy balance on this differential control volume. So I'll pause here for 5 seconds, and I'll give you guys a chance to draw the differential control volume and set up the energy balance around that. Okay, so let's look at an arbitrary section of this cylinder, and we'll zoom into a differential control volume there. So let's say I want to look at this cylinder here. This is at some location X down the cylinder. And here I'll draw another cross section. And this is at location X plus delta X. So if I zoom this out over here, it looks exactly, it's the same cylinder, except the length here is different. So if here, usually you'll know, let's say the length of this fin, you'll be told it has some length L. If it's a cylinder here, we know the radius or the diameter. And here, I said that this is at location X, and this was at location X plus delta X. Now the question is, what is this length? And that you can guess is just delta X. It's just the difference between these two positions. And what we want to do is now perform. So this is our differential control volume. It's differential because it's in terms of this delta X. And the reason we'd want to do a differential control volume is that we can use calculus techniques to derive differential equations in the end. So once we have our control volume, then we'd want to perform an energy balance. So how would we perform an energy balance here? Well, so remember how, conceptually, how does an energy balance work? The generic way to think about it is accumulation equals inputs minus outputs plus any generation. In this problem, we're going to assume no heat generation inside the fin. All we have is heat conduction down the axis of the cylinder, and on the outside we have convective cooling. So each of the surfaces that we have to identify if there are inputs and there are outputs. So let's first look at this one here. What we know is heat is conducting down from the base through this cylinder. So that means there's going to be an input of heat via conduction, which I'll call Q, the heat conduction flux, so Q double prime sub X. And this is at location X. Now we do the same thing at the other side and ask, what's going on over here? Are there any inlets on this side? Well, we know here that heat is conducting through the cylinder, so now it has to be exiting the side of the cylinder. And this heat conduction is also in the X direction, but it's evaluated at X plus delta X. Here we have an inlet. Here we have an outlet for heat conduction. And let's say in this problem, we are cooling down this fin with air. So how do we describe the heat transfer happening on this surface? So first, you have to ask yourself, what is that surface? How do you describe that surface area? And the surface area, the outer surface area of a cylinder is, if you remember, is 2 pi times the radius times height. In our case, the height is delta X. So we're gonna remember that. And now we have to ask, how do we describe that heat transfer? So it's convective cooling, and the general way we model that is using Newton's law of cooling. And Newton's law of cooling is written as the following. So it's just some heat transfer coefficient multiplied by the temperature difference of your object and the air. And so I should have mentioned in this case, let's just think about this whole problem as we're cooling down this base. So this is air that's at a lower temperature than our base. And so the objective is it's cooling things down. So now that we had 3 different surfaces here. We had the circular faces where heat conduction is happening, and then this outside cylindrical surface area where convection is happening. So now that we identified all the modes of heat transfer happening at each of our surfaces, we can put them into this conceptual formula we have here of inputs minus outputs plus generation. In a problem like this, we're not going to care about too much about the transients. So this is a steady state problem. And so here, then the left-hand side, there is not going to be any energy accumulating in the cylinder. It's going to be 0. And first, let's talk about our inputs. So I mentioned that we have heat conduction as our input at location X. And now we ask, do we have any other inputs? And we don't. So now let's focus on the outputs. So for outputs, we said we have heat conduction at in the X direction at location X plus delta X. It's a minus because it's leaving the other side of that cylinder. Now remember, these are heat fluxes. So if we want to get a heat rate, we'd have to multiply these by an area. So what would be the area term here? The area term will be the cross-sectional area of that surface. And this surface is a circle. So the area of a circle will just be pi r squared. So that's our conduction term. Now, if we're getting anything, and we are, we have to include our heat, the convective cooling part. So here we'll have sorry about that. So here we'll have our convective part. So that convective part is going to be the Newton's law of cooling, heat flux. I'm not going to put the formula in yet. We'll put it later. But now multiply again by an area. And what is that area? It's going to be the surface area of that cylindrical sheet. So it has a circumference of 2 pi r, and then multiplied by the height. And that gives us that outside sheet area. And that here, this height is delta x, which is the length of this cylinder. And so this is our formula this would be our energy balance, but now we have these delta x terms, and we're going to do some calculus to get rid of those. And also, we said there's no heat generation, so this would be the correct energy balance. So on the next page, I'm going to rewrite this, and we'll continue to solve this. Okay. So what we can do first is add the convective cooling part to the other side. So we'll have heat conduction term here. Equals the convective cooling part. So normally in these kinds of problems, if you haven't seen something like this before, what you normally do is, if you have like these delta x terms, you want to get rid of them. And so what you do, we're going to divide them both sides by delta x. And so now we have the following. Okay. So that's good. Now the question is, well, what do we do next? How do we simplify this term? So this is where we're going to use a little bit of calculus. So this stems, what we're going to use is the limit definition of the derivative to help us with this. So first, it would be helpful if we recognize what the limit definition of the derivative is. So this is the limit definition of the derivative. So it's some function f at x plus delta x minus f of x divided by delta x. And once you take the limit as delta x goes to 0, that gives you your derivative. Now, the important thing to see is can we make the connection? Like, how do you make the connection between these two? If you look, it looks kind of similar. We have an x term here with an x here. We have an x plus delta x term here with an x plus delta x. We also have a delta x and delta x here. So it looks very similar. The problem is, you see how the signs are swapped. We need the x plus delta x on the left side and x on the right side. So what we can do is factor out a negative from the formula. And so that's what this will look like over here. So don't pay attention to the right-hand side yet. We're gonna just focus on the left-hand side. So if I factor out a negative, now I get the x plus delta x on the left side. Okay, great. So now this resembles very closely to what we want to get, because we want to ultimately relate this to a derivative. So what we can do is now take the limit of both sides. So here we can just say, take the limit as delta x approaches 0 of the heat conduction side. And also you have to take the limit on the other side as well with the Newton's law of cooling. But the nice thing here is there is nothing here that is changing with delta x. So this is just going to be the same thing. What's going to change is the left-hand side. So I'm going to go to the next page and I will rewrite what we have just written down earlier. And I will also factor out a negative sign here. So earlier there was negative sign inside. I took the negative sign outside of the limit. And I said that because the right-hand side of the Newton's law of cooling did not have any terms related to delta x, it's just going to be the same thing. So it's going to be that Newton's law of cooling times 2 pi r. So this here, that is, if I write down the limit definition of derivative one more time, this exactly resembles the derivative of a function. Right, so let's just circle the terms one more time. So we have an x plus delta x here. We have then subtracting a term evaluated at x divided by delta x. So here what you do next is this limit then just becomes just you're taking the derivative of the thing, of the function inside. And that function is our heat flux. And here it would be multiplied by, and then don't forget the cross-sectional area term. And this equals Newton's law of cooling. What we can do next is plug in our different formulas for how we model the heat conduction and the heat of convection. So here we'll use Fourier's law for the heat conduction. So Fourier's law, if you remember, is negative thermal conductivity times temperature gradient in x direction. And Newton's law of cooling is heat transfer coefficient times a temperature difference. So if we plug these in, we get the following. So what we can do here is these negative signs will cancel each other out, and thermal conductivity, another common assumption you make, and this is a fair assumption, is that you can assume thermal conductivity is not a function of x, it's this constant throughout the fin. So you can also factor that out. And then what you're doing is now applying the derivative to the temperature derivative. So you should get a second derivative with respect to temperature times cross-sectional area. And I will rewrite this in the next page, and I will subtract now this h times 2 pi r, the Newton's law of cooling part, back over to the left-hand side, and this whole thing will then equal to 0. And usually in books, what you do is you leave your highest order derivative term by itself with no coefficients. And so we'll divide out k times cross-sectional area to each term. So what we get is the following. So there you go. This is the differential equation that you arrive at the end. And if you want, you can, so that's what I wanted to cover. To solve this problem, you'd have to understand how to solve second order differential equations. Usually the solutions to these are given in generically in textbooks. So like the general form of the solution to this kind of differential equation. And then once you have that general solution, you can apply the boundary conditions I mentioned earlier, which is that we know the temperature of the base and that there's no heat, that the end of the cylinder at x equals L is insulated. So this is that first problem that I wanted to solve.